Section: Introduction. In this section, we introduce the transformer architecture, which has had a significant impact on deep learning across various fields by improving performance and scalability. The use of attention in processing text sequences was highlighted in the transformer paper, leading to the development of models like BERT and GPT-3 that demonstrated the scalability and performance improvements with larger model sizes. The transformer has replaced LSTM and many natural language processing (NLP) tasks and CNN in the vision domain with models like Vision Transformer, VIT, and Conformer. Attention has become a key architecture for extracting meaningful information from data, leading to advancements in multimodal fusion such as combining text and vision in models like DALL-E 2 and Flamingo. Attention has also shown success in fusing audio and text in models like Audio LM and Gemini, which integrates text, images, audio, and video into a single generative model effectively. Despite Attention's success, it has limitations such as quadratic complexity with respect to context length, making it challenging to model long contexts efficiently. To address this, sliding window attention was introduced for handling infinitely long sequences, but it has limitations in capturing information beyond a certain window size during sequence generation. Various approaches like sparse attention and linear approximated attention have been proposed to handle long context problems, but they may not perform well at the scale of models like GPT-3. Neuroscience research has linked attention to multisensory integration and working memory in the brain, suggesting that attention plays a crucial role in both multimodal fusion and working memory. Working memory is essential for temporary task performance and is distinct from long-term memory stored in weights. We propose a novel transformer architecture, Transformer FAM, that incorporates a feedback loop to enable attention to work on both sequence data and latent representations, leading to the emergence of working memory within transformers. This architecture change allows Transformer FAM to maintain past information indefinitely, making it a promising solution for handling infinitely long input sequences in large language models, LLMs. Transformer FAM does not introduce new weights, enabling the reuse of pre-trained checkpoints. Our experiments show that fine-tuning Transformer FAM with LoRa significantly improves performance on long context tasks across different scales of LLMs. Section Summary. In this section, we introduce the transformer architecture's impact on deep learning, particularly in natural language processing, NLP, and vision domains, replacing LSTM and CNN, respectively. Attention, a key component of transformers, has shown effectiveness in processing both homogeneous and heterogeneous data, leading to advancements in multimodal fusion. To address the limitations of attention, we propose Transformer FAM, a novel architecture incorporating feedback loops within transformer blocks to naturally introduce working memory, enabling efficient processing of infinitely long sequences without introducing new weights. Section: Transformer FAM. In this section, we will discuss Transformer FAM, which stands for Feedback Attention Memory. We will explain the concept of block sliding window attention, BSWA. When dealing with long context inputs, there are two main approaches. The first approach involves increasing the context length by using more computational resources. The second approach is to implement sliding window attention, SWA, which is shown in a figure. During inference, the standard SWA implementation allocates key and value cache twice the window length initially. It then uses a ring buffer to update the necessary components at each step to avoid memory allocation and copying operations, which are computationally expensive. Big Bird introduced a variation called Block Sliding Window Attention, BSWA. BSWA caches information on a block-by-block basis without masking out past keys and values in the ring buffer. BSWA has two key parameters: block size and memory segment. The block size determines how many tokens are in each block and is also used as the sliding stride. The memory segment determines how many past blocks to cache. In our experiments, we set the default parameters as a block size of 1024 and a memory segment of 3, corresponding to a window size ranging from 3073 to 4096. When a sequence input is given to a vanilla transformer layer, the transformer transforms the input into a sequence output. The autoregressive transformer modifies the self-attention equation. In a transformer with SWA, the equation is adjusted to consider a window size of W. In a transformer with BSWA, tau represents the block index, and each block tau contains a set of keys and values based on the block size. The algorithm for transformer BSWA describes how to iteratively calculate A_T and concatenate the results into an A_tau sequence. Standard implementations typically use a causal attention mask for parallel computation of self-attention. Transformer XL introduced the stop gradient technique for the memory segment, but we argue that this technique hinders the model's ability to attend to past information effectively. While implementing BSWA may seem to increase training memory and computation, it does not significantly affect performance due to gradient checkpointing in LLM training. Transformer with sliding window attention has linear complexity with respect to the input sequence, which is more efficient than the quadratic complexity of the standard transformer. In inference, transformers with SWA or BSWA only need to cache a fixed ring buffer, consuming constant memory regardless of the generated token length. This allows LLMs using SWA or BSWA to generate infinitely long output tokens. However, BSWA has a limited receptive field, which can be addressed by our proposed architecture, Feedback Attention Memory, FAM, discussed in the following section. Section Summary. In this section, we introduce Transformer FAM, which leverages block sliding window attention, BSWA, to efficiently handle long context inputs. BSWA optimizes memory usage by caching information on a block-by-block basis, allowing for attention to all information in the ring buffer without masking past keys and values. This approach maintains a constant memory footprint during inference, enabling LLMs to generate infinitely long output tokens while addressing limitations in receptive field size. Section: Feedback Attention Memory. In this section, we hypothesize that by focusing on the feedback loop, we can create working memory. To achieve this, we introduced Feedback Attention Memory, FAM, by incorporating feedback activations into each block of BSWA. FAM is designed to fulfill several key requirements: integrated attention, block-wise updates, information compression, and global contextual storage. By adding FAM to block segments and integrating it into self-attention processes, our proposed architecture allows for richer representations and dynamic propagation of global contextual information across blocks. During self-attention within a block, the input query attends to the input key for that block, the memory segment, and the previous FAM, providing a more comprehensive representation than BSWA alone. Simultaneously, the FAM query compresses the current block based on previous global contextual information and propagates this information to the next block. This process optimizes the utilization of global contextual information throughout the model. Although the formal description of the FAM process may suggest increased matrix operations, in practice, it performs the same number of operations as BSWA due to efficient implementation. The use of vectorized maps for self-attention within blocks ensures that the causal relationship between blocks does not impact training speed or memory usage significantly. Transformer FAM maintains memory consumption and training speed similar to Transformer BSWA, even with the incorporation of additional FAM considerations. By reusing existing LLM checkpoints, Transformer FAM proves to be a general solution for LLMs, demonstrating its scalability and efficiency in training large language models. Section Summary. In this section, we introduce Feedback Attention Memory, FAM, as a mechanism to enhance working memory by incorporating feedback activations into each block of the architecture. FAM is designed to integrate attention, update block-wise, compress information, and store global contextual information, leading to richer representations and dynamic propagation of information across blocks. Despite the additional considerations for FAM initialization and length extrapolation, Transformer FAM maintains memory efficiency and training speed comparable to Transformer BSWA, making it a valuable tool for large language models. Section: Data. In this section, we aim to explain the ideal data needed to train Transformer FAM. We require a long document with continuous context, like textbooks or novels, to train Transformer FAM effectively. This document should be large enough to fine-tune a language model, LLM. It is crucial to use the same long document continuously in each training step while maintaining FAM and memory segments. The goal of an LLM's loss function is to minimize the difference between the model's probabilistic predictions and the actual data distribution. This difference is measured using the Kullback-Leibler divergence, KL divergence. To estimate the KL divergence accurately, we need to draw samples from the true data distribution, assuming they are independent and identically distributed, IID. However, the ideal training setup for memory training goes against the IID assumption, which we call the curse of IID. Due to this challenge, we struggled to find suitable training infrastructure or data for memory training. As a workaround, we used FLAN instruction data, which contains up to 8.5K tokens. Unlike the FLAN paper, we did not use a special attention mask to prevent attention between different segments during self-attention. Instead, attention occurs causally within the window, regardless of the segment. Our expectation was for Transformer BSWA and Transformer FAM to learn to remember important information and forget outdated details on their own. Each token in the FLAN data is assigned a weight, where a few shot examples and instructions have a weight of 0, and answers have a weight of 1. This setup ensures that the model focuses on generating the correct answers. To encourage the model to remember long contexts, we randomly selected 256 consecutive tokens from the 8.5K tokens and added them to the end of the data with a prompt indicating a repeated random segment. These repeated tokens were given a weight of 0.1. We hope that future research can use more suitable data, such as long continuous documents or speech, to train memory effectively. Moving on to the Pasky retrieval task, which is a common benchmark in long context transformer studies. In this task, a Pasky is provided at the beginning, followed by a long filler context. A question related to the Pasky is then asked. This task helps assess if information can be transmitted effectively in a long context. However, it mainly focuses on transmitting small but crucial information and does not test the efficient compression of large amounts of information. We fine-tuned the FLAN Palm 1B model for 5K steps using the Pasky format, with filler contexts ranging from 2K to 18K tokens randomly. We utilized Transformer BSWA with varying memory segments and Transformer FAM with no memory segments and a FAM length of 64. Transformer FAM successfully solved the task with filler contexts of up to 260K tokens, showcasing its effectiveness. In comparison, Transformer BSWA's performance improved significantly up to a certain number of memory segments before saturating. We also observed that Transformer FAM outperformed Transformer BSWA on various long context tasks, demonstrating its ability to compress and retain crucial contextual information within extensive contexts. Furthermore, we evaluated Transformer FAM and Transformer BSWA on larger models and found that Transformer FAM showed scalability as the model size increased. It performed slightly better than Transformer BSWA on GPT-3 tasks, which was unexpected given the task lengths. This improvement is attributed to Transformer FAM's efficient contextual representation by offloading data to FAM, reducing duplication within input activations and optimizing latent space usage. In conclusion, using FAM for compressed contextual representation alongside BSWA memory segments is recommended for LLMs to enhance performance across different tasks and model sizes. Section Summary. In this section, we focus on the ideal data for training Transformer FAM, which requires a very long document with continuous context, such as textbooks or novels, to fine-tune an LLM. Despite the challenge posed by the curse of IID, we utilized FLAN instruction data for training, where attention occurs causally within a window, aiming for the model to remember important information and forget outdated details. Additionally, we evaluated Transformer FAM on long context tasks and found that it outperformed Transformer BSWA, showcasing its ability to effectively compress and retain crucial contextual information within extremely long contexts. Section: FAM length. In this section, we observed that in the FLAN 1B model, performance on scrolls Casper, scrolls quality, and XL sum tasks saturated when the FAM length reached 64. Surprisingly, performance actually decreased when the FAM length went beyond 64. This indicates that compressing information is more effective when there is limited space available. According to Miller's law, people can typically hold around 7, plus or minus 2, items in their working memory at once. This limited space is not a flaw but a deliberate feature. In the figure labeled Transformer_FAM, the input query pays attention to the FAM, referred to as attention to feedback. The input query can focus not only on the immediately preceding FAM but also on earlier FAMs. The table labeled FAM_blocks displays XL sum scores for different numbers of previous FAM blocks. Increasing the number of blocks did not show a significant impact because the previous FAM already contains all the previous information through feedback. Therefore, the default setup only attends to the immediately preceding FAM. In the ablation studies presented in subsection Ablation, we explore additional experiments due to space constraints. Previous attempts to introduce feedback mechanisms in the transformer involved passing output activations from the top layer to lower or intermediate layers. Since the top 3 layers mainly focus on output reconstruction, we believe there is a substantial gap in representation between the top and other layers. Our proposal suggests a feedback mechanism between intermediate layers, unlike previous approaches that compressed information block by block without infinite propagation. Prior work has utilized recurrent cross-attention between blocks to enable the transmission of compressed information to subsequent blocks. Moreover, integrating feedback from a few upper layers has been used to incorporate past information. We introduced Transformer FAM based on the idea that the human brain processes various types of data using the same attention mechanism across different brain regions. Additional related works are discussed in the appendix, related, due to space limitations.